So our goal for this lovely day is that we are going to know and use the definitions of, don't forget that this is pronounced sign like a road sign. A lot of us like to look down here and we see this word here, sin, which means literally to miss the mark. And that's not what we're talking about. We're not talking about sin and doing bad things or not doing good things, which would be the other side of sin. All right, but we're talking about sines, so make sure to say it correctly. Next, we're talking about cosine and tangent. And specifically, we're going to look at how they are ratios of sides of a right triangle. So I wanted to jump into section 5.1 first before we get into the functions of sine, cosine, and tangent. Right now, we're just going to talk about the definitions relative to a right triangle. So let's see if we can recall, what does Sohcahtoa mean? And no, it is not Pocahontas' cousin. So as we are looking through this, the sine of an angle is equal to opposite over hypotenuse. So opposite over hypotenuse. Then cosine is going to be the cosine, and I'll just use the letter A for now, is equal to the adjacent over hypotenuse. So we'll review this by using a diagram momentarily. And lastly, tangent, which is abbreviated tan of some letter, some angle, is equal to the opposite over the adjacent. Remember that the magnitude of this angle right here, it could be in degrees. I could say the cosine of 45 degrees. Or I could say the cosine of 1/8 of a revolution. Or I could say the cosine of, pi over 3 radians or something like that. So A right here is about magnitude. So it could be usually radians or degrees. Today we're going to focus on degrees. Some things to consider. First off, where do things come from? The word sine, you do not need to know the etymology of this, but sine simply just means curve or curved or bent. It comes from the Latin for bend. Hence, you might know this, your sinuses. What are your sinuses? They go in your nose and they bend around and that kind of stuff. So that's where we get the word sinus. Sinusoidal. Sinusoidal just means up and down like this. A person who is indecisive could be described as mentally sinusoidal, where they just keep going, or abulic would be a good, abulic's a good word. Abulic means psychological dysfunction. They can't make decisions. Like someone at a restaurant for like 20 minutes. No, I can't. All right. So all that is there. Cosine, co just means with. So of course it's another curve situation, just different but the same. And lastly, tangent literally means to touch. To touch, tough. To touch, and geometrically, we talk about here is a circle, and tangent would be the line that touches the circle. So think of the road relative to a tire touching it. The road is tangent to that. Now, this definition of tangent does not always directly flow into trigonometric tangent. So I honestly don't know where the word tangent, why it relates to in trig this way. I do know where it comes from geometrically, but trig I'm not quite sure. So if any of you brilliant folks figure that out, let me know. All right, so let's take a gander here relative to theta. So most of this is review. So if this is my angle theta, then opposite is this side over here. BC is my side over there. That's opposite. Hypotenuse is always opposite the right angle, and hypotenuse is Greek for to pull tightly. To pull tightly.
Is that string of
And lastly, adjacent just means next door, as we might think. There's more to it than that. But the adjacent side, relative to theta here, adjacent is next to, oh, but Swenson, isn't hypotenuse also adjacent? The answer is yes, by the most simple definition of adjacent, but the hypotenuse being opposite the right angle here supersedes the other adjacentness of the hypotenuse there. All right, so it looks simple like this. In this diagram, if we're specifically talking about theta, this angle here, down A, as opposed to B. If you were up at B, it's completely different, okay? But I'm here at A, and it's all relative to A. Okay, so in this case here, it would simply be the opposite over the hypotenuse. And in this case, would be segment BC over segment AB. Now, generally, those are going to be numbers, 5 over 9 or 10 over whatever. Notice that the hypotenuse is the longest side. It will always be the longest side, just by the nature of triangles here and the nature of right triangles. Hypotenuse is the longest side. So that means this will always be less than 1 right here, because it has to be larger in the denominator. All right, continuing on, cosine, not cos. Please don't say cos. It is cosine of theta. And in this case, of course, co is adjacent over hypotenuse again. And in this case would be AC over AB. And lastly, tangent, toa. Tangent, of course, means opposite over adjacent. And lastly, that would be BC over AC. I do want to point out to you that opposite shows up twice, hypotenuse shows up twice, adjacent shows up twice. So all of these are used, and this is a specific ratio about how not just one triangle, but every single triangle on the planet will always have the same ratio right here. Whatever theta is, if theta is 15 degrees or 10 degrees, it will always make a similar triangle. Why do I know that? If you recall from basic geometric principles, if this is congruent to this, so both of those are the same theta, and that's congruent to this right angle, then by angle-angle similarity, the two triangles will always be similar, and since the triangles are similar, that means the ratios will be the same as well. In other words, the proportion, it will always be in proportion. So that is why these ratios will always hold true. Why these ratios will always hold true for a specific theta. All right, so let's practice a little bit. What we want to do is spend some time calculating what is the sine of t. So here's t. So starting from t, I have to calculate what the sine is. So, of course, sine means opposite over adjacent. So it's 14 over 50, which we can calculate to be exactly 0.28. Next, the cosine of t. Again, it has to start relative to here. So the adjacent is 48, and the hypotenuse is still 50. This one calculates to be exactly 0.96. And lastly, my tangent of t. Again, we start here, and the opposite over the adjacent. So it's 14 over 48. I'm going to use the approximate sign here and punch that into my calculator. Okay. So 0.291. I do want to give you a heads up here. I do want to give you the heads up when we are calculating the ratios here. This is an exact answer. This is an exact answer. And when we use fractions or decimals, because we often will, please go out not as far as you can, but maybe to the 10,000ths. That's to 4 decimal places. 10,000ths. Often we'll go out. This one didn't go out because this is an exact number. 0.28, that's exactly correct, so I don't have to go further. Don't have to go further. But if it does, if you do have to round it, generally speaking, let's round it to the 10,000ths place, which is to 4 decimal places. All right, you do not need to draw a diagram here, but if you would like to, it might be very helpful. And how are we going to find the sine, cosine, and tangent? Actually, go ahead and take a moment to draw this, because you do have to find out the third side using Pythagorean theorem, and then calculate these. All right, so just by way of review, we only have 2 side lengths. We know that angle D is the right angle. So after we set up our triangle, we can determine that our second leg there has to be 9 using Pythagorean theorem. Then using 49 and 41, we can come up with our ratios here. Remember, rounding them if need be. These are exact answers, and rounding is often what we're going to be using. Either we have this to begin with, or we get to it. So I do want you to be fluent in both directions there. So, trigonometry is used all over the place to find out where spaceships crash land on the planet, to find out witnesses reports, to find out where an event occurred, a fire, for example. Sonar uses trigonometry all the time. So let's just walk through to see how the trigonometric ratios can be used. So sonar in a salvage boat locates an object at a downward angle of 50 degrees and a distance of 510 meters. So how far below the sea level, or the level of the water, is the object? So generally speaking, make sure we're going to make a diagram. We will probably have to erase the diagram as things change. We're going to label that diagram accurately and then set up the trig ratios to solve. By the way, we don't always have to use all the ratios. So it's not necessarily plural. We're just going to find the one that's most appropriate. So let me just set it up. Boat is here, and this is my amazing boat. Very geometric. Okay, now there is some sort of object underneath. That's not, looks like a finger there.
Yeah, I was going to say.
I cannot draw for the life of me. This is a rocket ship or a shark, so, but it's down there. Let's just say it's a spaceship from the future that's landed down there and they happen to acquire it. Okay, now from the sonar unit, which is anywhere on the boat, it doesn't matter, it says it's 50 degrees until it hit it. So that means relative to the surface here, theta, right there, theta is 50 degrees. And here's essentially what we're trying to find. We're trying to find the distance down that this thing is. It is always safe to assume that up and down is always right angles. Distance from something is always right angle. Distance for a line and a point. Distance from will always reach at 90 degrees. Okay, so notice what we're trying to find is how far below the level of the water is the object. So I'm trying to find this distance here. I do know this right here. It's 510 meters. I don't know this, and it turns out it's irrelevant. I don't know the distance from the boat to directly above on the water. Again, that's going to end up being irrelevant. So the question is, which trigonometric ratio are we going to use? Well, let's see here. Relative to theta, the distance I'm looking for is opposite. And the thing that I know is hypotenuse. So if this is opposite and this is hypotenuse relative to theta, what is the the ratio that I'm going to use? So we are going to have to use the sine. because Sohcahtoa says the sine of theta is opposite over hypotenuse. It's the thing we're looking for and the side that we know. So let me go ahead and clean that up now. I'm going to say sine of 50 degrees is equal to opposite over hypotenuse being 510. How do we solve this? Here's the nice thing about your calculator is all you have to do is multiply by 510 on both sides. And in your calculator, you're going to do this. Sine of 50 times 510 or 510 times the sine of 50. I am going to make sure to use parentheses because if you don't put parentheses around the sine, it might try to multiply the 50 with the 510 first. And now when I plug this into my calculator, I get that x is approximately 390. Now, since my unit is meters, I don't need to go super far out. So 390.7 will be fine right there. Meters here. Now remember, this is a word problem, so we need to bring it back into the real world situation. And that's why I put the unit on it, but just conceptualize it. That means that this shark thing is just slightly under 400 meters. For those of us who need to convert, a meter is slightly larger than 3 feet. So this right here would be a little bit more, maybe 1,100 feet under the water. So as we are drawing on example number 4, my apologies for the sting there. It should say string. The 60-meter long string of a kite you are flying is being pulled taut, that's tight, by the wind and makes an angle of 68 degrees with the ground. Okay, so clearly we have the ground and we have 68 degrees. Remember, don't simply just start drawing like this. Don't just simply start drawing like that. Remember, 68 degrees is fairly specific. You don't have to do a perfect situation, but if you draw this, you're wrong because that's clearly closer to like 30. So remember that 45 would be halfway, right? So 68 would be somewhere like that, okay? So make sure to be somewhat accurate when we are sketching. Now, it's not going to be drawn to scale because I don't have enough room here. Well, so my kite is up here somewhere, like that. Okay, there's the string. And notice all parts of the triangle that get formed here. This is directly above, so that's the altitude. So we're told it's 60-meter long string, so we know that this is 60 meters right here. And the question is, how far from you, so you are flying, so this is me right here. Now, it does say it's 60 meters with the ground, whatever that means. Does that mean I am sitting on the ground and holding it down? Well, people often do that with kites. So that's probably the situation or something like that. And then there's a person standing over here. And how far from you would a person be if that person is directly underneath the kite? There we go. Now we have an accurate situation, and we're looking for this distance right here. We're looking for this distance here. And we know this to be 68 degrees right there. So tell you. All right, so as we look at relative to me here, where my degree is, I could say cosine being adjacent over hypotenuse there. So the cosine of 68 degrees is equal to the unknown over 60, like so. Now, if the question said, how high is the kite? You would be finding this right here. If the question said, what's the angle up there? Then you would use something else. By the way, you don't have to use 68. You could use this angle right here. This is just a side note. But what's the relationship between this angle here and this angle here? So because the two acute angles of a right triangle, are complementary. This one is 22. So you could do the sine of 22 opposite over hypotenuse instead. Just giving you an alternate way to do it. All right. Then let's go ahead and solve this. Remember that when I solve this, I'm multiplying both sides by 60. And then setting your calculator, make sure your calculator is set to degrees. Before we even attack this, though, how would you estimate this right there? So we know that this here will be less than 30 because this here is greater than 60. And now when we do find it, x is approximately what, 22?
22. I got 22.47.
22.5 meters. And of course, that does make sense relative to the situation here. It doesn't ask us the height here, but we have the opportunity. We could easily find the height. From here, you could use sine to find the height or Pythagorean theorem. Because you have a 60, you have a 22.5. The problem with Pythagorean theorem is that you already have an estimate right here. So using an estimate and then squaring it and then taking the square root of the sum or the subtraction, this right here might be further away from the answer than you expect. So I'd probably use sine to find that. All right. The next example, we'll use the concept of the elevation of depression or the elevation of, the angle of elevation. And essentially right here, this right here is called the angle of elevation. Because relative to the ground, this is the angle that something is up. So if the sun is over here, that's the stupidest sun ever. And of course, a person is standing there and the shadow is being created. Then the angle of elevation would be the angle of the sun, essentially, the angle of the sun. So we use something called angle of elevation, just to show what that diagram looks like. If you have something up there, and here is the reference point, then the line that connects them, this right here, is the angle of elevation. And generally, it's not necessarily relative to the ground, but it is relative to horizontal. So it's relative to horizontal. So in a sense, the inverse is true as well. If we're talking about the angle of depression, if I had an imaginary horizontal line right there, then this right here is the angle of depression. So if you are standing in an airplane, so here you are in an airplane, and you're just looking straight, so this is the horizontal line, and whatever angle you look down at, it's this angle right here that is called the angle of depression, not the angle. So oftentimes we might confuse and say, oh, look, it's the angle from inside here, but rather it's from the horizontal compared to this line. Both of these go from a horizontal. And what also is true is since we have parallel lines cut by this transversal, we know that these two have to be congruent. Alternate interior angles are congruent. So angles of elevation and angles of depression are actually going to be congruent. And they're both relative to a horizontal line of sorts. Generally the ground, but doesn't have to be the ground here. And this is the horizontal parallel to the ground. All right, so look at this example here, example 5. A woman wants to estimate the height of a silo. So she walks 60 feet from the silo and estimates the angle of elevation to be 38 degrees to see the top. If her eyes are 5'3" from the ground, how tall is the silo? All right, so we've got a silo. And she walks 60 feet away, like so. And it says that she looks up 38 degrees. So the angle of elevation to see the top is 38 degrees. Now I do want to point out my diagram's off, so I'm going to have to fix it and extend it. Remember that it tells me where her eyes are. So that means this is where the perspective comes from. So that means I need to extend my silo a little bit to the ground there. And we're also told how far she walked. There, 60 feet. The apostrophe again means feet. So we're looking for this height here. However, the triangle is this here. The triangle is this here. So it doesn't include this lower part. So once we find out whatever x is right here, using sine, cosine, or tangent, we then have to add the 5 foot 3 inch eyeball to that, or the height of the eyeball to that. So that will be the caveat, the slight difference here, is that we have to add the 5'3" to it. All right, now let's see which one we're going to use. So we have 38 degrees here. Here's my opposite, and I know adjacent. So my opposite adjacent, that's going to put me with TOA. So to set up, we say the tangent of 38 degrees is equal to x over 60. Coincidentally, multiply both sides by 60 and punch that into our calculator. So x is approximately 46.9. Sometimes the instructions will say round to the nearest whatever, but it doesn't say what to round to, but we're not done yet. It just says how tall the silo is. Since we're dealing with feet, then whole feet or a tenth of a foot is reasonable, but we certainly wouldn't go to hundredths because we don't need micro inches at all. Now, we're not quite done. We do have to add the 5'3". Now, how...
You can't add it like that, right? Because it's in decimals, not
Good,
inches.
good. These are different forms, so it's difficult to add. So the one has to be converted to the other. So mechanically, how do we add these together? Well, let's see here. In order to convert this one to decimals, so remember 3 inches is 3 over 12. So that becomes 1/4. Or you could just plug in 3 divided by 12. That's fine too. So 0.25. 0.25. So now we have 5.25 there. And then we add those together. So the height is approximately 52.15 feet. Now, you can convert the 15 to inches if you wanted to, but my guess actually here that if you just rounded it to 52 feet, then that would be a reasonable answer. Just simply 52 feet is a reasonable answer on this one.